Thank you. In this work, I was going to talk about our work in CT scan registration with 3D dense motion field estimation using LSGAN. By myself, Isa Anas, Ahmed Onsy, Bogdan Matuszewski from Computer Vision and Machine Learning Group in School of Engineering, University of Central Lancashire. The presentation outline consists of lung registration problem, previous approaches, proposed registration method, results, and conclusion. Registration is defined as an estimation of a geometric transformation aligning objects such that the distance between objects' corresponding point is minimized, bringing the objects into alignment. In the non-registration framework, this transformation is usually estimated through solving the following optimization problem. U, in this case, is the estimated deformation field or displacement field, which is subject to some fidelity function plus some encoded smoothness, in this case, regularization. The key challenges for lung registration include large deformation, existing of rigid and deformable structures, sliding motions between the organs. Each of these characteristics requires a specific transformation properties. In this case, we will need a network that will be able to identify each pixel and its belonging to an organ, and based on that, to do the necessary transformation. Traditional registration algorithms are formulated as an iterative optimization problem. These algorithms often provide detailed modeling of motion properties. However, they frequently require a varied number of iterations as the cost function is optimized each time for specific data. Therefore, the necessary computational time is difficult to predict, what makes these methods unsuitable for application where interactivity is an important property of the system. More recently, Eppendorf presents a supervised approach using sliding window to directly estimate the registration error. Young also used a sliding window technique to estimate the deformation field for 3D brain registration. The main problem with the batch-based learning is the lack of information about the global context necessary for correct representation of small local deformation and, in the same time, large displacements. The reviews of deep learning techniques proposed for medical registration are available in reference 4 and 5. Balkrishnan and others presented voxel morph for MRI deformable brain registration. Recently, Fang and others present a deep learning model for unsupervised deformable thorax CT scan registration, and that has some similarity in the network design to our network with different training schemes. Outline of the proposed solution. A 3D deformable displacement field is estimated using both local and global representation with a 3D CNN training on the full-size CT volumes using contractive expander network model. A discriminator is added to the network during the training to utilize the GAN paradigm training. Introducing the LSGAN to the network improved the training and increase the performance of the network on the test sets. The generalized Charbonnier loss function is used for both the fidelity term with the image intensity differences and the regularization term with the displacement gradient. The network is optimized with Adam optimizer with starting learning rate of 10 to the power minus 4 and with Sapphire weights initialization. The network structure is shown in the figure. You can see that the network consists of generator and discriminator, and the sizes of the volume are shown in the input and the output of the generator. The breakdown of the network is shown in the list shown. You can see that the network input consists of 2 channels as the input, 2 channels for the input, which is basically the concatenation of the moving image volume to the fixed volume. The output of the generator is basically a channel or a volume of 3 channels, which represent the deformation field or the displacement field for X and Y, Z component of the vector of the displacement. The discriminator in this case is basically a classification network that consists of sets of convolutional 3-dimensional convolutional neural network, but in details they are listed on the right of the figure. You can see that we are using 3x3x3 convolutional neural network, patch normalization, Lee-Kiralou, average pool. The loss function that we use consists of 2 sets. The first set is related to the generator, and the second set is related to the LSGAN loss functions. For the generators, we use the generalized Charbonnier loss function for fidelity estimation, and we calculate the gradient of the motion field or displacement field to calculate the smoothness of the field. And then we added up the two losses in equation 3. To train the network in a GAN setup, we use equation 4 to train the discriminator and equation number 5 to train the generator. In this case, the total loss function that we use to calculate the generator consists of 2 parts, which is the summation of equation 3 plus a scaled version of equation 5, as shown in equation 6. The training set consists of Cretis datasets, copied Guinea datasets as training during the training phase. The dataset being augmented with small deformation and forward and backward estimation, which duplicate the data volume. The data test sets that we use consist of Derleth dataset, which is basically common in this field as a benchmark for the evaluation. As a result, first we show the benchmark, we are showing the landmark that provided by the data sets, and on the left you can see that it shows that before the deformation, before the registration, and on the right we show when we obtain the displacement field and we apply it on the landmark in the way that you can see in the right side of the figure. The list in the figure here shows that what we obtained and what we compare to the previous results. On the left is the cases that the Derleth dataset contains. In column 2, we have the registration or before registration, the target registration error. Then the result that obtained from the reference 13, which is related to the iterative method. Then on column number 4, we have the registration using convolutional neural network in reference number 7 that lately reported. Column number 5 and number 6 is basically our results. Here we can see that we obtain already on the model before GAN implementation 1.3 mean and 1.7 standard deviation target registration error compared to the previous method. With the GAN implementation, we actually improved the result to 1.13 in the mean and 0.67 in the standard deviation, which basically means how the network generalization improved by using the GAN implementation. This is the histogram of the target registration error. The only thing that we could look at carefully is case number 1, which is considered to be one of the simplest registration case in this data set. Our model didn't perform very well with that, and we will justify it later in the next slides. This is another representation of the target registration error before and after the registration, encoded for each volume. You can see that we need to have all these points to go as close as possible to the horizontal line. And also, it's good to mention here, volume number 8 shows a very scattered distribution compared to the rest of the volumes, which is one of the reasons why we are actually focusing on that volume in our results. This is another representation for the deformation field or displacement field layout over the image of volume number 5 when we try to warp it to volume number 0. So we are warping an exhale volume to an inhale volume. You can see that the diaphragm is moving with the displacement field downward, which actually trying to register to the inhale case as it's shown. Back to volume number 1 or case number 1, our network accept 128 by 256 by 256 by 128 volume depth, while the volume provided by the DERLAB case number 1 consists of only 94 slides. So we needed to pad the rest of the volume, and apparently the model find it as a kind of strange way of feeding the data and provide us with more error than usual for this case. Although it tried to perform properly in some of the places during the registration, as shown next to diaphragm area. In conclusion, a novel deformable volume registration method has been proposed using contraction expansion 3D CNN configured without and with discriminator subnetwork within a GAN training framework. Without LSGAN, the 3D CNN network trained with the Cretis and the copied Guinea dataset achieved 1.3 and 1.7 mean and standard deviation target registration error. The same network with discriminator trained using LSGAN achieved 1.13 millimeter and 0.6 millimeter standard deviation on the test set. The proposed method outperformed alternative method reported in reference 13, where they reported 2.11 and 0.9 for mean and standard deviation target registration error respectively. Furthermore, the model outperformed the recent reported deep learning model reported in 7, where authors achieved 1.89 and 1.94 mean and standard deviation target registration error. The proposed method seems also to be competitive in terms of the computational time, as it enables to estimate the entire 3D registration volume field within 19.3 milliseconds. The future work will be focused on better understanding of the role of the discriminator and changes to the configuration of the described model to directly reflect intensity differences between corresponding points in the exhale-inhale sequence of the lung CT scan. Thank you.